Okay, so we need to be able to measure the head gradient in the soil. And we saw in a previous video that we could measure the head using a tensiometer. This is going to function like a piezometer in the soil, except this porous ceramic cup right here allows water to flow out and in, so we can exchange water between the tensiometer and the soil. But we don't exchange air. This ceramic prevents the entry of air, at least up to fairly moderate soil suctions. And so we can use this thing to measure the pressure head at the porous cup. And if we know the pressure head, then we can determine the total head by adding in the elevation head. So here's an installation of a tensiometer. Here's the porous cup. And there's a gauge up here. And we use that gauge to measure what the pressure head is here down at the porous cup in the soil. And we've got some simple formulas for doing this. This is the total head, the elevation head, plus the pressure head. The gauge reading is given right there in centibars, and we multiply by minus 10 to change the units from centibars of suction to centimeters of pressure head. And so that's going to define the units that we're using as centimeters. And so then the pressure head is equal to this G sub P, which is the gauge reading in units of pressure head in centimeters. And we add in the depth below the gauge where the porous cup occurs. And let's see, this D got cut off a little bit, so there's D. So that gives us the pressure head, and then the total head we get by adding in the elevation head. So what we've done is just establish a datum here, and we get the elevation head above that. Okay, so that allows us to get the pressure head at a tensiometer cup. Now to calculate the hydraulic head gradient, we include another tensiometer. That'll give us the hydraulic head at 2 points. And if we define a coordinate z going up, then we can have measurements at 2 points. And what we assume is that the hydraulic head is only varying with the vertical direction. And so these tensiometers are going to be put quite close together. And so we ignore any kind of horizontal variation and assume that the variation in head is only due to variations vertically. And so we can take the measurements at these two different points and use then a finite difference approximation for the derivative to get the gradient. So if this is 0.1 and this is 0.2, then we would have a head at each one of these points. And so here's a formula for the head at 0.1. We use the elevation and the depth and the gauge measurement at each one of those points. There's also the formula for H2. And then the gradient is given using this finite difference expression. So it's just simply the difference in the head at these 2 points divided by the distance between them, the vertical distance, L. And if we do this, then we get the head gradient with respect to this vertically pointing coordinate. Okay, so that'll give us a positive head gradient or negative head gradient with respect to this upward coordinate. And that'll be important when we're using Darcy's law, because then we'll be able to tell that in this case, a positive gradient would be the head increasing with z. And so a positive gradient would plot like this. So if this is z and we plot h, then a positive gradient would be like this, where the head is increasing with z, and that means that the flow would be downward. A negative gradient would be just the opposite. where if there's Z and H, the negative gradient would be that the head is decreasing with Z, and that means that the flow is going up. Now, in the vadose zone, we can have flows going either way. Typically, flows will be going up if we're having evaporation at the surface dominating. They'll be going down if there's been a rainfall and we have infiltration and perhaps recharge going on. Tensiometers are often grouped together as clusters with the porous cups set at different depths. This is useful because it allows you to measure the pressure head at different depths. You can determine then the hydraulic head at different depths. You can determine the head gradients. You can estimate whether the water is flowing up or down. And if you know the hydraulic conductivity, you could even then estimate what the flux is. So this is a table that has data from 5 tensiometers. They're completed at different depths, and you can see the different depths here shown in the first column. The next column shows the gauge reading on each of the tensiometers. And then the table is set up with different headings that will walk you through the calculations that will be required to determine the pressure head, the elevation head, and then the total head, and the head gradient. So the first step is to do this column to get the gauge reading in units of centimeters of head. So the gauge is in centibars, which is the same unit that's used in the gauges for the tensiometers that we'll be using. So this table will walk you through getting the total head, and then you have this last column that will be used to calculate the hydraulic head gradient. So if we have a hydraulic head here, H1 and H2, then we can calculate the head gradient here as H2 minus H1 over L. And so we do that for each one of these rows, and then we leave out the last row here because we wouldn't have a second head to use to calculate the gradient. And so with these 5 tensiometers, we can calculate these 4 gradients. Now, if we set the coordinate system as upward, and we could say that's the z coordinate, then this is a finite difference expression for the gradient, and we would be using, if we put the gradient right there, we say that that gradient applies at 30 centimeters depth, and we're using 30 centimeters depth and the value at 60 centimeters depth, which is behind it. So this would be a backwards difference in the finite difference schemes of calculating gradients. Okay, so that's what we can label it. If you've used finite difference methods before, this is a backwards difference. We can also just see how it works conceptually as a difference in hydraulic head over a difference in depth, and in this case the L would be the distance between these two tensiometers, which in this case would be 30 centimeters. Okay, so this will allow us to calculate the hydraulic head. We can do a couple of things though before we get there. We can just look at the list of the total head, and we can see where the highest hydraulic head is and where the lowest, and we know that the flow is going to be from highest to lowest, so we can get the direction of flow just from looking at the relative magnitudes of the hydraulic head. We can also look at the relative magnitudes of the pressure head. Now, one thing about these tensiometers is that they work in the vadose zone, but they also will work in the saturated zone. So tensiometers are capable of working below the water table as well as above it, and so they can be used to identify the location of the water table. And remember, the water table is defined as the location where the pressure head is equal to 0, and so here we'll have a column of pressure heads, and so we could we might get a depth, a tensiometer reading of 0, but we might get a reading where this is say minus 10, and this would be plus 5, and we could then infer that the water table occurred somewhere between these two readings. We could probably interpolate between them and get a depth estimate. Okay, so this is the table. What I want you to do is fill this out and see how you do. Go and calculate all the gradients. Assume that that z is up when you calculate the gradient. And so if you're doing that, and this value, say, is 10, and this value is 50, then the head is decreasing in the z direction, so that would give you a negative gradient. Okay, so let's see, do all of that and do the calculations, and then you can check yourself. I'll post the results as a separate file on the module, so go ahead and work this out on your own. When you get the results, then check them and see how you do. One last thing, when you're doing these calculations, you'll have tensiometers at several depths. And when you're calculating the hydraulic head, you can always determine the datum for the head calculations wherever you want. So I would recommend that you pick the datum to be equal to the depth of the shallowest or the deepest tensiometer. So pick the datum to be equal to that depth. When you do that, z for this tensiometer will be 0, and z for the next deepest one will be equal to 30, and so on. That'll make the calculations a little tidier. We've just seen how we can measure the hydraulic head gradient in the vadose zone using tensiometers. So if we can determine what the hydraulic conductivity is, then we can use Darcy's law to estimate the flux. So the hydraulic conductivity in the unsaturated zone works somewhat differently than it does in the saturated zone because it changes with the moisture content. So to see how that works, let's take a look at this idealized diagram here. So this would be some, this is a bundle of capillary tubes, and so these are just straight tubes, but we're imagining that these tubes represent the range of pores that are in a porous medium. And so we've got some big pores and some small pores, and we've just straightened them out just to make the visualization process more convenient. Now, one thing that we recognize is that the hydraulic conductivity, it's going to be proportional to the diameter squared of the pore. That's something that we saw earlier. That comes from that comes from just concepts that we saw for the saturated zone. So that's a general principle. And then the other thing that we need to recognize is that when we pull tension on these pores, that will drain them, and what happens is that the surface tension holds on to the water, and it provides some resistance to draining of the pores, and it provides more resistance to the smaller pores than the larger ones. So when tension is applied to a soil during the drying or draining process, the large pores drain first, while the smaller ones remain filled with water. We apply more suction, and then the next size class drains, and so on. Okay, so with that in mind, let's take a look at this scenario over here. And what we've got is 3 different pores of different sizes, and they're filled with water, so the soil is saturated, and we've applied a hydraulic head gradient shown schematically here. And so this is the head drop over the length of the soil. And what we're going to do is a conceptual experiment where we drain the soil, and so the water content's going to be reduced, but we maintain the same head gradient. And we could do this in the laboratory by adjusting the conditions, but we're just going to imagine what would happen if we did that here conceptually. So we have these 3 different pore sizes, and the effective conductivity for flow through these pores depends on the diameter squared. So if we double the diameter of the pore, then we increase the hydraulic conductivity by a factor of 4. And so what we might imagine then, if we have the same head gradient on all of these pores, there would be different flows through the different pores. And so there would be more flow through the biggest pores and less flow through the smaller ones. And we just see that schematically. Okay, so now let's pull some tension. And we do this by draining out some of the water. And remember that the big pores will drain first. So what happens then is we start to drain the water out, and this big pore drains, and all that remains then is water that is around the edge of the pore wall. So there's still some water in there, but it's just now a thin film. And so we could have some water flowing through that film, but there'll be a lot of resistance to flow now. And so there'll just be a small amount of flow through this pore. Even though it's a big pore, it's drained out, and we can only have water flowing through this thin film. So now we've pulled some tension on this, and we have what amounts to now a smaller flow. So if we add up all of these flows, the total flow is smaller, and we see that the most of the flow, or the larger, this pore in particular, has more flow than the larger pore. It has basically the same amount of flow as it did before because it remains fully saturated, and we've held the head gradient the same. Okay, so if we look back at the conditions where this pore was completely saturated, we could take that flow and divide by the head gradient, and that'll give us the saturated hydraulic conductivity. In that case, the suction, because the pores are completely filled, let's just assume that the suction is 0. So the suction would be right here, and we would plot that as the saturated conductivity. So we would plot it right there. Now we've pulled some suction, we've drained the largest pore, and we have a lower flow rate. And so remember, the hydraulic conductivity will be the flux divided by the head gradient. So in our experiment, we're keeping the head gradient the same, and so as the flux changes, the hydraulic conductivity must be changing. And so we've pulled suction, and now we've got a lower hydraulic conductivity. So if I plot that, let's say this step right here is at that suction, and the hydraulic conductivity plots right there, a lower value than we had before. Okay, so we can continue. We'll pull some more suction, and we'll drain out the next pore size. So as we pull suction, actually we'll drain the larger pore down to just a very thin film, and this next pore size drains out as well. And so what will happen then is the flow through that pore will just dramatically decrease. And now that we've applied this extra suction, what we see is that the pore that is supporting the most flow is this one, this smaller size. Altogether, it's a lower flow than we had before, and so the hydraulic conductivity has dropped some more. So if that's the suction where we are right now, we might say, well, that's the hydraulic conductivity. Okay, so it's important to recognize that even though the soil is only partially saturated, we still have flow that's going through it. It can go through films along the pore walls, but it also can go through the pores that remain completely filled, and these pores are progressively smaller as the soil drains. Alright, so what that does is it gives us a picture of hydraulic conductivity as a function of suction that is varying like this. So it's decreasing with suction. And if we take a look at some plots of that, if we were to carry out this experiment and get a variety of points and plot it up, we would see that the curve looks something like this. The points that I had before would have been like this, and so we have some more points and it decreases down. And what we find is that the hydraulic conductivity will decrease by a lot, by several or perhaps many orders of magnitude as you apply suction to a porous medium. So often this axis is displayed as a log scale to account for that wide range of variation in hydraulic conductivity. So here's the plot of hydraulic conductivity as a function of suction. Sometimes we see it plotted as a function of pressure head, and so suction is negative pressure head. So if we took the same plot and plotted it as a function of pressure head, it would look like this one here, a mirror image. And there are several different functions that are used to describe the hydraulic conductivity as a function of the pressure head. The one that we'll use, because we can estimate the terms in at least one of the characteristics in the field, will be the Gardner model. And this is for the relative permeability. And remember, we can get hydraulic conductivity from permeability. So the Gardner model says that the relative permeability of water is equal to 1 for pressure greater than the air entry pressure, and it equals to this exponential function for the pressure less than the air entry pressure. So remember back from the soil moisture characteristic curve that this was the air entry. So even though we have some suction right here, some negative pressure head, the pores remain saturated. So if that's the case, the pores remain saturated, then we're not really altering the flow through those pores, and so the hydraulic conductivity in the Gardner model stays the same. But once we reach this point, the air entry pressure, then we start draining pores. The air enters the porous medium. We change the flow structure within the porous medium, and we have a decrease in the hydraulic conductivity. Now, the way this is set up, P is the pressure in the porous medium. And so alpha, that parameter there, has units of 1 over pressure. And what we're implying is that P is negative. Okay, so we're doing this in terms of the pressure in the pore space. It's negative, and so what we get is that this will be, as P becomes increasingly negative in that direction, then this function decays off as a negative exponential. And so we see this plot right here. Okay, and so that allows us to determine what the permeability is as a function of the pressure. And actually, what we'll be able to do is what we'll want to use is the hydraulic conductivity. That'll allow us to determine the flux. So what we could do is simply plot this and simply say that's K sat. So we could say that K equals K sat times e to the alpha P minus P air entry. Okay, so if we can determine the saturated conductivity and we can determine alpha, then we can determine what the hydraulic conductivity is at a particular pressure. And we'll be able to do those things in the field with various different types of measurements.